In the last video, we learned how to find the length of a vector projection, which is not the same thing as a vector projection itself. We called that actually a scalar projection of a vector. A little bit confusing. But now we're finding actual vector projections. We're doing the exact same thing. We're imagining our wire and the sun is directly overhead or perpendicular to the vector that we're projecting down onto. And we're going to find this vector here, but we're going to acknowledge that the direction of the vector that we're shining our light onto is relevant. And the new vector that we come up with will have length and direction. So we already know that the length of our projection is this. This is a formula that we've just used. So to turn this into a proper vector, all we need to do is multiply it by the unit vector x. Now that's here, and it's got a unit length. So that means it's a length of 1. So all we're really saying is, all right, if we know how long this is, let's say we've got an interval that's 4 units long, then we would be able to say, all right, it's going to be 4 lots of whatever this vector is. Now this vector will have its own direction, remember. It's only 1 unit long, so we need to do 4 lots of it. But we're effectively just multiplying our scalar quantity, 4 or whatever it is, by this unit vector. Now we know that to find a unit vector, all we need to do is take vector x, which goes along here for however long, and divide it by its distance, because that will give you something that's got the same direction but only is 1 unit long. So we can take this part here and we can say, all right, we've got our length, let's multiply it by that, but in fact let's multiply it by this version because it's a little bit easier to use. So we've got the part that we know and we've multiplied it by the unit vector. Now we can tidy this up in a variety of ways. You could use it just like that, that's fine, ready to go. But on the denominator here, we're going to have the length of vector x multiplied by itself. Now, if we take the length of vector x and multiply it by itself, you could use that formula a squared plus b squared all in the square root. But then we're squaring it, which means we've just got a squared plus b squared. And really, that's exactly the same as just finding the dot product using the x vector and itself. So it's written, I think, a little bit more simply by just swapping that out for the dot product. So we end up with this slightly unusual looking formula that's really quite easy to use. We have the dot product of our 2 vectors on the top, and on the bottom we have the dot product of the vector that we're projecting onto and itself, and we need to multiply that whole thing by whatever that vector that we're projecting onto is. Now it will have its own formula. It might be in component form, like 3i minus j, something like that, or it might be in column form, or you might have this vector as 2 points and you've got to put it into column or component form yourself. Okay, now for some examples. We need to find the vector that results when vector A is projected onto vector B if we have these 2 different scenarios. Now I've written our formula up here and I've put the version of it that's got A's and B's in it so that we can get used to subbing in different letters. So nice and straightforward, let's just go ahead and sub in all of our parts, then we'll sketch it to check whether this makes sense. So the projection of A onto B is equal to, now we need the dot product of these 2, which means we need 12 minus 2, that's 10, over the dot product of B and itself, which means we need 4 4s, that's 16, and negative 2 times negative 2, that's 4. So that gives us 16 plus 4 is 20. And then we need to multiply that by vector B itself. Now vector B is in component form. So if we're given it in component form, then we'll put our answer in component form. So clearly we can see that 10/20, well that's a half. So we've got a half of this. Now that just means with our distributive law that we do a half of 4 and we do a half of negative 2. So our projection is the vector 2, negative 1. Now let's see if this makes sense if we sketch it. Now our vector A looked like 3 steps across and 1 step up, something like that. So that's A. And vector B is 4 steps across, so it went just 1 step further. So this is 1, and it went down 2. So let's say something like this. Doesn't need to be perfect, but we're getting the idea here. Let's just label that as 3. That's 1, that's 2, and this is vector B. So if we're projecting A onto vector B, then what we're getting is a projection that comes down like this and meets B at right angles, and we're seeing that it's going to have the same direction that B had, and the length is going to be whatever this length is here. So our new one is actually going across to get from here to here. How would we get there? Well, we'd go 2 steps across, 1, 2, and 1 down. And certainly even just on my rough sketch, that looks about right, that this could be 2 here, this distance, and this distance here would then be 1. So that looks like it's on the right track and makes a little bit more sense, I think, if you sketch it. Now that's just checking your work. Once you get used to these and you feel like your process is okay, you don't need to sketch every one. But obviously if it's, you know, not quite sinking in what it is that you're doing, I think a sketch is really helpful. Okay, so for this one, we need to find the projection of A onto B, and we need the dot product of A and B, which means 4 lots of -2, and -1 times 5 is on the top, and on the bottom we've got -2 times -2, and 5 5s on the bottom, and we need to multiply that whole thing by vector B. Now it's in component form, so we'll keep our solution also in component form. We need those there. So now what do we have here? -13 over 29. So we've got -13 29ths of -2i plus 5j, and we can expand our brackets there and say -13 times -2 is 26. So let's just finish it over here. We've got, hang on, I need a better pen. We've got 26 29ths I, and multiplying this by 5, 13 5s is 65. So we've got -65 29ths j, and that is our solution. Now if you're solving more difficult problems, sketching it is really a good idea. Here I've got vector u, 3i plus 2j, so clearly it's going across about 3 units and up 2. Perhaps this isn't perfectly to scale, but it's a rough enough picture that will help me. And I've got vector x, which goes across 5 units and up 1. So if I project u onto x, then what I'm finding is this vector from here to here. So let's go ahead and do that. So projecting vector u onto vector x, I need to do the dot product of the 2 vectors, which is 15 plus 2, over the dot product of the vector I'm projecting onto and itself, which is 25 plus 1. And then I need to multiply that by the vector I'm projecting onto, so I end up with this. So my vector is a little bit awkward. What's 17 5s? That's 50 plus 35, 85 26ths I plus 17 26ths j. A little bit awkward, but there's my new vector. Now that's my new vector that sits here. So this vector, let's just all of that, it's here and it goes that way. And it's got this direction. So if I was asked, say, for this vector, let's say this one here, going from here to here, don't forget you've got all the information that you already need, and you can solve these sort of problems quite easily. All you need to do is say, well, how do I get from here to here? I need this vector and I need the negative version of this vector. So now if we label this point here, that's O, that's A, let's make this point N. Sorry, my sketch is a little bit messy. So then to get from this point N to A, the directed interval NA would be my new vector, 85 26ths I plus 17 26ths j, except this goes forward, so I'm going to need to reverse all of it. So I need to actually go backwards along that one, and then I need to add the other vector. Now obviously you could start by adding the other vector and then subtract this one. It makes no difference which way around you go. But now tidying up here, the number of i's I have is 3 minus 85 26ths, which gives me -7 26ths I, and the j's I have is 2 minus 17 26ths, which is 35 26ths j. Now that's a little bit more than 1, and this is just a small amount. So what we're saying is that to get from this point here to this point here, I'd need to go left 7 26ths of a unit, and then up 1 and a bit units, which looks about right even on my very rough sketch. And lastly, let's quickly just look at the distributive law and how that works with projections. It works pretty well as you'd expect. if we've got some scalar quantity making our original vector that we're projecting bigger, then it makes sense that the projection will just be bigger. So clearly here, if I've got u being projected onto x, then my new projected vector is going to look like this. Whereas if u was twice as big, then my new projected vector would also be twice as big. I think that makes sense. And when we're projecting something, they don't have to have the same tail. So for example, if I was just projecting here vector v onto vector x, the fact that they don't have the same tail coming down, I don't really need to see this part of it to say, all right, vector v starts here. So the projection of it is going to land there, all right? So if I'm projecting vectors u plus v, then here's u, here's v. Obviously u plus v is this vector here. Now I can actually just make that vector u plus v if I want to and project that down, but I can also project u and get this vector here, and then project v and get this vector here. And if I add those two vectors together, then clearly I'm going all the way from here to the end.